Good afternoon, morning, evening, whatever time zone you're in. Welcome to the SciPy 2021 second day tutorials. We're going to start the tutorial Bioimage Analysis Fundamentals in Python. And Nick, go ahead and take it away.
Thanks very much. I'd like to also introduce Kira Evans, who'll be here helping answer questions as well. Kira, you can say hi. And yeah, really happy to have everyone joining us today. I think, I see the people in the session is still rising, so we'll get started slowly as folks start to join. I'm going to share my screen now. All right, hopefully folks can now see my my screen. And so it's really my pleasure to be giving this SciPy 2021 tutorial on bioimage analysis fundamentals. The GitHub repository can be found here. Kira can add that. If you can add that to the chat as well, please, that would be great. The repository, there are installation instructions here. I recommend folks get started with the installation now if you haven't already done so. It can take a little bit depending on the approach you take to build the environment with Conda. But you have instructions here for cloning the repository, and then building the environment with Conda, which is I probably would recommend. You can also try with pip2. And then there are some instructions for checking your installation too. If you run into problems with the installation, please post in the chat as well, and Kira can help. So, overall, in this tutorial, we're going to explore some of the most critical Python libraries for scientific computing on images. We're going to go through some of the fundamentals, like linear filtering, convolutions, using scikit-image. It's a foundational Python library for image analysis. And then we're going to use Napari, which is an interactive visualization tool for looking at some images and interacting with them. And then we're also going to talk about how we can extend these concepts to data sets that are larger than RAM using Dask as well. And yeah, that's sort of it. You just quickly see on the chat. All right, so I see, it seems like the number of folks in the session is still going up a little bit. So I'll leave this up for another moment or two. Once you've installed this repository, you can, we're going to be teaching using Jupyter Notebooks, and so you can launch a Jupyter Notebook. For the final lesson, you have some optional additional data sets that folks can use, which there'll be some breaks later that people can download them as well. People can download the slightly smaller one as well if they just want to get started with that. And again, a little bit more about today's session. I'm imagining that we're going to spend about 5 to 10 minutes now in this intro period as folks join. And again, here's the repository. And then get going with this lesson number 1. People will also notice that there are 2 copies of all the notebooks. There's one that is unrun and with no solutions. There's also one with the solutions. I recommend, if you're interested in a more interactive experience in these tutorials, going through the ones without the solutions. If you also, though, want to just kind of read along, there are solutions for a lot of the exercises in the solutions ones as well. Maybe I pause just to, if there's any, Kira, if there's anything folks are running into in the chat. It's hard for me to sort of monitor the chat at the same time, but I'm not getting any red flags. So yeah, maybe we'll sort of dive right into to the first lesson. But really, please, folks, ping if you're having a tough time getting going. And as I said, it's really my pleasure to be teaching today about bioimage analysis fundamentals in Python with scikit-image Napari Dask friends. So in this first notebook, we're going to be looking into image filtering. Before we get going, we just have to run some magic commands to ensure that our plots are going to be rendering in the right way. And so that's that first cell there. And as said, this first lesson will focus on image filtering. So filtering, it's one of the most basic and common operations in image processing. You can filter an image to remove noise, enhance features. It could be, the desired result of your analysis, or just a pre-processing step along the way. But regardless, it's a really important topic to understand. And so the first thing we're going to look at is local filtering. And just to get going, I'm going to import matplotlib pyplot as PLT and numpy as NP. And for folks that aren't familiar with matplotlib, that's a foundational plotting library in Python. And for folks that aren't familiar with NumPy, that is a foundational array library. And we'll see that arrays and images really have a lot in common. So what does local in local filtering mean? Well, it really means that you're adjusting a pixel value by looking in the neighborhood of that pixel and the values surrounding that pixel in that neighborhood. And so the surrounding elements, they can be identified or weighted based on some, kind of like footprint, sometimes people call it, or a structuring element, or a kernel. These are all different words that come from different communities. So to begin, we're just going to look at a really simple 1D step signal. And I think, someone could be asking, well, why are we looking at, 1D things? I thought this was going to be about image processing and images are more than 1D. But really, looking at things in 1D, it gives you great way to kind of build up an intuition that is going to generalize to 2D, 3D, and beyond. And so we're going to start here looking at a 1D signal. Let me just quickly check the chat again. Not that I'm going on, but it looks like, yeah, we've got about 50 folks joining us, and so far so good. So 1D plots, you can see here we've got a very simple step function. We started off by just making an array of zeros, 100 zeros, and then we set the second half of those to be a 1. And so we have a nice step. We made a little figure and a little axis with matplotlib, and then we plotted the step signal and we adjusted the margins a little bit. And so this is a very clean signal. This is sort of a very ideal signal, but maybe now we're going to add some noise. And just to make sure we all see the same results, I'm gonna have this random seed, which is setting the random number generator. So if I run this cell now, what do we see? So we have created our noisy signal, which is our step signal plus this random noise. And here we're using the normal distribution to generate the noise with a mean of 0, standard deviation, I think that's standard deviation of 0.35. And this is saying what shape we want this signal to be. We're asking it to be the same shape as our step signal, which is 100. And we're adding them together. We're going to create a new plot, and we're going to now plot our noisy signal. And so, given a noisy signal like this, I think one of the very first things that one might want to do is ask, how can you recover that original signal underneath it? And again, the same ideas that we're going to be using here to look at 1D signals are going to generalize as we start moving up to 2D, 3D, and beyond signals for images. So if we think about, okay, what is the simplest way to recover something that looks a little bit more like the original? Well, one approach is we can just take the average between neighboring pixels. And so, averaging is going to reduce some of the noise, and using neighboring pixels means that we're not going to blur things out too much. So we can just handcraft this right now. We can just write, all right, I'm going to grab the noisy signal going all the way up to the last pixel, and then the noisy signal starting at the first pixel and going all the way to the end. Add them together, divide by 2 to average, and plot the result. And you can see right away, okay, this already begins to look a little bit smoother than the previous one. So What happens if we want to now take 3 neighboring pixels? Well, we can do the same thing. We'll take from 2 to the end. We'll take a little bit in the middle, missing 1 on either end, and then we'll take from the second pixel through to the end. Now we have to divide by 3 because we've got 3 things. And so you can see, all right, the mean of 3, it's gotten even a little bit smoother. And so maybe this seems like a really good approach, but you think you can quite easily see that, for averages of more points, that expression just keeps kind of getting on hairier and hairier, so it's going to get longer and longer. And you also have to worry about what's going on at the margins. You'll maybe notice that original signal was length 100, then we went to length 99, now we're at length 98. Something is going on. And so, I think it's, we can ask a question, is there a better way to do this? And it turns out there is. This same concept of nearest neighbor averages, it can be expressed as what's called a convolution with an averaging kernel. And that operation that we did with smooth signal 3, it can be expressed as follows. So create an output array of the same length as the noisy signal. At each element, starting at point 1 and ending at point -2, you place the average 1/3 to the left, 1/3 at the exact same, and 1/3 to the right. And then you discard the outer leftmost and rightmost elements. And so this operation, this procedure, it's called a convolution because the input image and the array 1/3, 1/3, 1/3, it's being mixed together in this way. So now we can try and write this in a new cell. First, we're going to create this convolution kernel, 1/3, 1/3, 1/3. We can use the np.full operation to do that. And then we can use the np.convolve to convolve the noisy signal, the mean kernel. We have to give it a mode as well, actually. It's referred to as valid. And we can then create a set of subplots, a subplot to look at this. So if we look now and we overlay them, we actually see that it is the same as what we'd seen before, and the signal is identical to before. So we can now look at this a little bit more interactively, and here we're going to use this little SciPy widgets example. SciPy widgets are a great way to get simple interactivity in Jupyter Notebook. And so here we've got a little convolution demo function that we've put together. And have a little filtering step inside it. For folks that downloaded the notebooks more than 24 hours ago, you might be missing this plt.show call. It's important to add that in there because otherwise you'll end up with making many copies of the same plot rather than being able to do what I'm going to do now, which is moving the slider along. And so in this plot, what we're really looking at is these 3 dots here represent the location of the convolution kernel, and then moving the slider is equivalent to kind of moving the kernel along the signal. And then the orange is the output, which is the average of these 3 pixels at that location. And so, the advantage now of the convolution is really that it's just as easy to take the average of 11 points as 3 points. And so now we can just, make a mean kernel of size 11. We can run otherwise everything the same again. You can see now this is much smoother, and we can do the same example looking here again. So we've got these 11 points moving around as well. So to take the mean of 11 values, we realize that we have to move further and further away from the edges, and then that's really starts to be a bit of a problem, and actually things are kind of getting a little offset and a little funny because of that. And so we can, instead of using the valid mode on the kernel, on the convolution, we can use the same mode instead. And so if we run this again and we look with the valid mode, we lose data at the edges. With the same mode, we've been able to recover a little bit more. but we now see some artifacts at the edge. They're less noticeable here, but they're very noticeable here. And that's because the same mode has actually padded the signal with zeros and then applied valid as before. And that's really not quite what we want in this case, because that might introduce a big artifact. And so you can sort of look at this again, though. Now we're using a constant padding, and you can see that I didn't add a plot.show. So everyone that runs this is going to have a little problem now, because I forgot to add a plot.show here. Now if you run this, you can see that I'm averaging much more accurately in the middle of the region. So that was an introduction to convolutions, which really form the basis of 1D filtering. We've got an exercise here, which if folks want to try, you can look up the documentation of the SciPy.ndimage.convol function, and then try and look at applying the same convolution, but using different mode keyword to avoid the edge artifacts. And maybe to kind of give people a little clue to get going, I'm going to import SciPy.ndimage has NDI. And then I'm going to you can do ndi.convolve ? And you can see the documentation in the notebook as well. So, maybe look at this a read. You can see the mode section right here, and give this a try. And so I'll pause for a moment. I'm also going to check out the chat and see if there's anything critical to respond to. All right, well, I didn't see anything in the chat, and so I hope folks are following along. And maybe let's talk a little bit now about what more additional options are available to us in the SciPy NDI convol. So if we look here, reflect, that's one of them that was not present before. And the reflect, the input is extended by reflecting about the edge of the last pixel. And so I think that's going to be much better for us, because for our step signal, we kind of want to get more zeros when it was a 0, and something that's a little bit closer to more ones when it was a 1. So let's give this a try right now. So I'm going to do smooth signal reflect equals ndi.convolve, and then I'm going to grab the noisy signal. I'm going to grab our mean kernel again, and now I'm going to do mode equals reflect. And then I'm going to just do our same little thing here, fig x equals plt.subplot. There are other ways to plot as well using matplotlib. This is just one approach, x.plot. And then let's take a look at this smooth signal reflect. So boom, look at that. And this is now much nicer. Put that little thing on there. And you can see that whereas before, if we go back up here, we saw this big drop off down there, big artifact at the edge. You can see right now we lose that. And so this looks much, much nicer now. And so, this is 1D filtering. This is one way now to recover a noisy signal. So if we go back, let's go back now, and let's think about, instead of a sort of smoothing and noise reduction, we can think about a difference filter. And so if we run this plt.subplots again, and then we grab our step signal, and we see a 0, 1, let's think about a way to look at differences in the signal. And so as an exercise, before we run these cells, maybe folks can try and predict what the convolution kernel with the -1, 0, 1 will do. And so really try and think about that before we run these next cells. Think about before we had a convolution kernel of 1, 1, 1 divided by 3, and now what will this kernel do? I'm just going to quickly check the chat again. Okay, so if we think about this, whereas before we were averaging together the three values, the one before, the one present, and the one after, what are we going to do now is we're going to take the difference between the one after and the one before. And so if my signal is flat and not changing, and I take the difference between the one after and the one before, well, my signal is flat, it's not changing, so I'm just going to get 0. And so when the signal is not changing, I'm going to get 0. Imagine now there's a big change, like our step function, and I take the difference between the one after and the one before. Well, that was a big change in that signal. And so if the signal became much, much, much larger, then I'm going to get a positive change. And if the signal became much, much smaller, then I'm going to get a negative change. And so let's run these. You'll actually see I'm going to use, there's both correlate and convolve, and I'm going to run them both. And you can see here that our step signal, when doing the np.correlate and the np.convolve, we've actually now pulled out either a positive change in the case of correlate or a negative change in the negative change in the case of convolve. And so it's sort of interesting that these two different methods actually have different sign conventions. And that's a little bit of a sort of technical signal processing reason that convolutions sort of tend to occur kind of back to front, whereas correlations tend to occur in sort of signal order. So we're going to use correlate from now on, because it's just maybe a little bit easier to talk about, but it's really not that different in this context from convolve as well. So as I sort of explained earlier, when neighboring values are close, the filter response is close to 0. But then at the boundary, we're subtracting a small value from a large value, or vice versa, do a large value from a small, and we get this spike in response. And so the spike identifies our edge. And again, we're just looking at this for 1D plotting right now, but one can imagine how we're going to start generalizing this to edge detection in 2D images as we go. So what happens if we now, we're going to look at the sort of the commutativity and associativity of filters. And so that's the ability to process A then B, or B then A, or the basic operations. And so if we first ask, okay, what would happen now if we tried this with our noisy signal? And so if we take our noisy signal and we just as is run our correlate function on the noisy signal, you can see that we actually don't really see that big a spike around where we know the step is. And it's basically taking a difference of the noisy signal has actually not done a very good job at giving us anything sort of meaningful here. We've actually just pulled out a lot of big changes, and that's really because the noise has contaminated that measurement. When there's high noise, it's much harder to find the spot where the signal changes. So we can record, though, that we actually smooth the signal by averaging with the neighbors. And so we can apply the two filters in sequence to combine their properties. So if first we run the smoothing filter, and then we run the edge detection filter, you can see that now we actually get a much better signal. So what am we plotting here? We've got the original signal, blue, the noisy one. We've got the change of just the noisy signal in dotted, and you can see that was what we looked at before. It wasn't very good. If we now look at the smooth change, you can see it's actually still relatively noisy, but right here, above these little lines that just kind of demark really for visual guiding purposes, you can see that the biggest change we've got of the smooth signal is at the origin where the step, not the origin, sorry, is at 0.50 where the step happened. Now, it turns out we can actually do this in any order. The convolution, it is associative, so we can we can actually do them together, and we can actually correlate the kernels themselves to create now just one kernel that is a smoothed difference filter. And so you can see it is wider than either of these alone. It's gone out to now be 5 pixels, and it's not itself as sudden a transition because it's doing both smoothing and differencing at the same time. And we can look and see, excluding the sort of pixel shift, it's given the same result, and we could take that into account if we wanted to as well. So that's a little bit about what have we covered so far. We've covered convolutions in general. We've covered averaging kernels, which is a way to remove noise. Now we've just recovered difference kernels, which are a way to detect changes and step functions. Next, we can look at some additional filters, such as the Gaussian filter. And so a Gaussian filter with a kernel with a variance sigma squared is given by this formula here. And it is essentially a smoothing kernel that has better smoothing properties than the mean kernel. And so we can create one from scratch here. And so run this. And so here we're actually doing some mathematics to create our Gaussian kernel. We can actually also look at, if we apply our difference kernel to our Gaussian, we can now look at the Gaussian difference kernel. And if we do our original signal convolved with the Gaussian difference, we can again see actually here that we recover at that 0.50 the largest transition. And yes, we do see some wiggles down here, but they are more in the noise. So Gaussian blurring, Gaussian filters, Gaussian difference kernels, these are all good operations to apply when denoising, say before edge detection. So that concludes the 1D part. I think, hoping everyone's as excited as I am to get to talking about images now, and 2D, which really are sort of 2D arrays. But I hope folks understand why going through the 1D signal processing was sort of was helpful, or see why it's going to be helpful. So again, we're going to be using NumPy, and if we just start with an incredibly simple image, which we can print here below. Really, what is it? It is an array, a 2D array of numbers. Here we've asked for one that is 7 by 7, and we have manually set a little portion to be different in the middle. And so if we plot this, and now instead of using the ax.plot command, we can use the ax.imshow command. We can see that there is a bright square in the middle. This is where the ones were. This is where the zeros were. And so we can now ask those same things that we did with our step function. We can now start looking at for our 2D image as well. And so the first thing we're going to look at is going to be the mean filter. And so now we're going to create a 2D array. So this is going to be a kernel that is 3 by 3, that has 9 elements inside it. So we have to divide by 9. If you recall before, we started with looking at kernels that were length 3, we divide by 3. Now it's 2D, we have to divide by 9. And so now we can take our mean kernel and apply it to every pixel in the image. And so applying a linear filter essentially means you center the kernel on a pixel, and then you multiply the pixels under that kernel by the values in the kernel, and then you sum those results, and then you replace the center pixel with the summed result. So this process is also known as convolution, and again, it's generalizing from what we were looking at in 1D to 2D. So we can import the ND image again, and we can look at our bright square. We can then correlate the bright square with our mean kernel. And if we just print these things and we look at them, you can see that our 1, 1, 1, 1, 1, it's sort of, gotten a little bit blurry in a sense. It's meaned in a sense. And it's now going from 0.111 at the edge all the way to 1. And if you again think about what was our kernel operation doing, it's each pixel here has been replaced by the mean value within the 3x3 neighborhood over that pixel. And so for the pixels right at the edge, they increased because they used to be 0, but then they got a little bit of this 1 here, and so they went up. For pixels that were here where they used to be 1, this has gone down because now it's got a bunch of zeros inside it, so they just kind of come together. And then the pixel that's right in the middle has actually stayed the same because the full convolution kernel, the 3x3 kernel, sits right on top of it here. And so really this principle of convolution, it's the same principle behind convolutional neural networks, or CNNs. And CNNs have been really popular in the past few years. And really, the only difference is that in the above, we use a simple mean kernel. In the convolutional neural network, the values inside the kernel are learned to find specific features or accomplish a specific task. And we have a little exercise at the end that we can do it as a demo there. So if we look, though, at now a little demo of the convolution in action, you can see here I'm moving, again, like in the demo before in 1D, when I was moving the convolution kernel across the image. Here I'm sweeping across the image. You can see that when I get to, say, this value, I've got 4 pixels inside, 5 outside, so I have a sort of intermediate value. Here I have only pixels outside, so I have the lowest value. And then in the middle here, I've got all pixels inside. So again, really the concepts that we learned in 1D, generalize here to 2D. Now let's take a look at our first sort of real image, and I think it's going to be very cool to see this with real images. So we're going to, from the scikit-image module now, we're going to import that data, and we're going to grab this camera person from their data. And we're actually going to look at it a little bit smaller. We're going to downsample it so I can do : 10 to get only every 10th pixel, and make a little plot of that here. And so on the left, we've got the full image, the full resolution image, which is 512 by 512 pixels. And on the right, we've got the downsampled image, which is 50 to 51 pixels by 52 pixels. And so we're actually going to be doing this sort of plotting side by side fairly often. And so we can actually construct a little helper function, imShowAll, down here that will do a little bit of normalization of the setting contrast limits, add some titles, and then plot the results. And so if we just kind of create that function, we can now look at applying our mean filter on a real image. It's very exciting. So let's take our pixelated data from before, and then if we run our mean kernel through it, and we compare the pixelated on the left and the mean filtered on the right, you can see really what's happened is that we've blurred things out. And so, it has become, in a sense, pixelation. It's a little bit of like a noise introduction into the image. We have reduced that noise, and the image has become much blurry as well. And so you've also lost the ability to see sharp edges, but you can see the outline of the person much more easily. So, and depending on what is trying to achieve next, that there can be pros and cons with that. So maybe now we're going to talk about some of the kind of essential filters for image processing. So most of the time now, there are many filters that folks have made over many years. The Gaussian filter is one of them, and we're going to use the SciPy filters. SciPy has lots and lots of filters that it ships with. And so here you can see we're just going to grab the Gaussian filter from it, and then we don't actually have to even use the NDI correlate. We can just run the Gaussian filter on the bright square with a certain sigma, and you can see that it's actually a little bit of a smoother transition even than our mean filter as well, and that's because of the shape of the Gaussian as well. And the sigma is what defines the standard deviation, defines that size of a neighborhood as well. Again, these are all kind of local filters. So if we run this now on our pixelated camera person, we can also see that it's done a nice job blurring that image too. So it doesn't look drastically different from the mean filter, as it said, but it's typically preferred because of this concept of distant dependent weighting, and it doesn't have any sharp transitions inside it. So a little tidbit for anyone familiar with thinking about things in a Fourier analysis sense, it's good to avoid sharp transitions because otherwise you can end up with artifacts. And so if you actually look at the full 512 by 512 image, you can see there are some differences, and potentially there's some like little more artifact-like things in the mean filter, which are gone in the Gaussian. So as you said, technically, the Gaussian filter, it's actually looking in both a distance at rows and columns from the center. That's this R's and C's, practically speaking, we can actually, we can truncate this Gaussian filter. Even though in theory it sort of extends infinitely far away, we can truncate it, and you can see that's been done here. Again, this is like a single point in the center, and this is the Gaussian profile. This is just a 2D plot. Maybe a fun thing for folks to try and do right now is plot the midpoint here. And so that's actually going to, if I plot this plot here, I can see a line. Just take a line through this. Maybe people can write here how to plot the 1D profile through that line. I'm going to check the chat again, see how things are going. Community infos is the section NP correlate. There's a question about why np.correlate is used in some places and np.convolve is used in others. I think it's really to demonstrate, in some senses, at this level interchangeability of them up to a sign difference. I think people use both terms, and there are different conventions associated with both of them. But here, but that's that. Let's see. The note we use convolve options on YN. Okay, great. So it seems like that there's some good discussions in the chat happening. Let's take a crack at this. So if we, again, as we've been doing before, make our little figure an X, we can do plot subplots, and we can grab, and then we can actually just plot x.plot. And then above this 2D image was the kernel. So if we just do kernel, we can grab a slice through it, and you can see here, okay, so this is what it looks like through the GAN. It's the Gaussian, and you can see it's really tailed off to basically being near 0. And so we can truncate the kernel just fine there. So going on to talk about some basic edge filtering. So for images, edges are boundaries between light and dark values, and the detection of edges, it can be useful on its own right, or it can be used as a preliminary step for other algorithms, which we'll see later. And so, for images, you can think about the generalizing the concept of different filters from 1D to 2D. You can think about it as an edge at points where the gradient is kind of large in one direction. And so we can approximate those gradients with the difference filters. And we can look at this in either the vertical direction. And so here in the vertical direction, or in, we can create our vertical gradient. And if we ask, okay, what's the shape of our vertical? It's 3, 1. So it goes rows by columns. And so we've got 3 rows vertical, and it goes -1, 0, 1, and then 1 row horizontal. And we've applied now this, we're using the correlate function again. Could also use convolve, but there's a minus sign. And you can see that we've picked out some edges at the top of the person and at the bottom of the person. There's some interesting stuff happening around the tripod, but all the edges are edges going in the vertical direction, top to bottom. So maybe as an exercise now, let's have folks try and implement a horizontal kernel. And so we can compute a horizontal gradient. And then if we can do that here, and then as a next step, let's try and compute the magnitude of the image gradient at each point, which is given by the square root of the sum of squares of the horizontal and vertical gradients. So I'll pause again for a moment. Let folks give these a try. Maybe have a quick chat and see in the chat. Right. And just as a reminder, we're scheduled to have another about 40 minutes for this lecture. This lecture was this tutorial was supposed to be about 17 minutes in total, and then there was going to be about a 10-minute break. I think we're doing actually pretty good on time, so we'll sort of see how things go. So all right. So the task was to create a horizontal kernel. And so if we start horizontal kernel, and so if the vertical kernel was 3 by 1, that means that we want the horizontal kernel to be 1 by 3. And so I need 2 sets of square brackets here because I'm making a 2D array. And then that first column is just going to have one thing in it, though. But then they're going to be 3 values, or the first row is just going to be 1, but they're going to be 3 values for the columns. So I'm going to go -1, 0, and 1. And then let's gradient horizontal, and then we're going to grab NDI.correlate again, and then we're going to use basically we're just doing the same thing that we did up here, the pixelated, we're casting it to a float, pixelated dot as type float. And again, the casting to floats, it's because when we're like averaging, we don't want to end up like doing lots of rounding just with integers. We now have to be in a space of floats. And then we're going to pass it in the horizontal kernel. And then let's try our same little routine of creating our little subplots, and then let's do an x.plot. And no, I don't want x.plot. I want x.mshow because I'm not plotting a 1D thing. I'm plotting a 2D thing. And I'm going to plot. I'm going to show the gradient horizontal. Okay, let's see that runs, and I always forget to do a little thing here. If you don't see it on the top, and so now we've done our gradient horizontal. And so if we look up above the gradient vertical, we can see that it's sort of a lot of edges top to bottom. If we look at the gradient horizontal, you can see that it's really a lot of edges left to right, and so that's really useful. What happens now if we wanted to compute the magnitude of the image gradient each point in time? I'll give, again, just another moment for folks that are doing this at the same time to type that in. All right, so if we think about what was our formula for gradient magnitude, it's this square root of the sum of squares. So let's type in gradient magnitude, and then we're going to do np dot square root, and then we're going to do np dot power, and then we're going to grab our gradient vertical, and we're going to put it to the power of 2. And then we're going to add in our np dot power, and now we're going to put in our gradient horizontal and power of 2, and then we're going to close brackets on our screen. Maybe I'm going to make these things 2 lines, a little bit nicer, a little bit more readable. And then we're going to do our same little trick, figure an axis equals lt dot subplots, and then we're going to do our x dot show, and now we're going to plot the gradient magnitude, and maybe this time I'm going to remember to put a little semicolon, and let's look at it. All right, and we got it. So now you can see this is actually looking really nice. I just love this stuff. It's you can see how we've pulled out both the edges all around the person right now, and if you compare where we started with these two, the gradient magnitude has actually really done a nice job here. And so, in fact, that this is so nice and so common that there are special names for some of this stuff. So the Sobel edge filter, it's probably the most commonly used edge filter. And if we, you can click on the docs for SciPy. I'll just kind of quickly go through that. And you can see a little bit here about what kernels the Sobel edge filter use. And you can see that's a little bit different than what we did. This 1, 2, 1, minus 1, minus 2, minus 1. You can think about what that difference is actually, how that's meaningful. And if we look at the bright square, we can see the Sobel edge filter as well. And this is the just kind of picking up the edge around here. So as with any derivative, noise can really have a very strong impact on taking a derivative, and so we might want to think about smoothing. And so if we look now against the gradient before smoothing, you can see how it's sort of fairly pixelated. But after smoothing, you can see how it's much cleaner. And really here, the same concepts that we were learning around 1D images are generalizing to the 2D case. So you can see how the edges look more continuous in the smooth image. And really there's a great, if I go to the SciPy filters, there's a great list of filters here that folks can explore too. So we've now got one little fun sort of neural network style exercise where if we pretend that we have an image and a ground truth of what we want to detect. So you can see here, all right, so we've got some source here. We're just going to say that, these are the things that we're interested in detecting. Could we use sort of a machine learning approach to find a 3x3 convolutional filter that recovers this target? And again, I just want to emphasize this is, really reduced introduction to convolutions and how they might work in a machine learning case. And so one approach that we can do is we can use this scikit-image function called view as windows to extract little patches of images. And again, if you want to get the help from view as windows, you can use that question mark trick that I showed earlier. Then we can use np.reshape to view the image as a set of approximately n pixels 3x3 patches. Think about why it's only approximate. We'll talk about that in a moment. Reshape them into patches and then a feature matrix, and then use a scikit-learn model to understand the relationship between pixels and the neighborhood. And then we can actually look and see, okay, during this process, did we actually, if we look at those model coefficients, how do they compare to the Sobol coefficient? So this is a little bit more of an involved exercise. I think it's just meant to be a little bit of fun. No worries if you're new to scikit-image and view as windows. If these or if you're not familiar with scikit-learn and it's a new library, this was just a really hopefully a kind of fun way to unify a couple of concepts. Here. So pause again for a moment as folks start thinking about that. Quickly check the chat. Oops, that's the Slack. Just a note, actually, for everyone, there is a Slack which is for this tutorial as well. Oh, yeah, little tricks about transpositions and things, all good things. Okay, so let's try this one. So from scikit-image.util, we're going to import the view as windows function. Actually do that same little trick before to look at its help. So what is this? Rolling window of an input of an n-dimensional array. Windows are overlapping, and this is a really nice way to extract little patches of the image. And so we're going to use this. I'm going to refer to this as a feature matrix X. So I'm going to call it X, and then I'm going to do my image, and we're going to give it a kernel 3x3, or not kernel, a shape 3x3. And if I just sort of run this and see what happens now, x.shape. Okay, so what have we done here? We have now extracted 510 by 510 3x3 patches of this image. So for every pixel, we have grabbed a 3x3 neighborhood. And so we've gone from a 2D array to a 4D array, where you can think of these 510 by 510 as indexing the pixels, and then the last one as the 3x3 as the size of each patch. Why is it 510, not 512? The same reason as when we were talking about the mode equals valid stuff at the very beginning of the exercise, edge effects, boundary effects. Okay, so what do we want to do now, though? Now we want to recast this into a kind of feature matrix. And so the first thing we can do is we can just, collapse these things. So I can just do, if I just collapse all the pixels, I can reshape into, and again, it's not necessarily the most efficient way to do this, but I can just do, -1. So if we did this, what would I have now? Okay, now, all my pixels have been collapsed into this, 260,000 little pixels. And then actually, though, I want to, reshape my 3x3 things into a just a set of 9 features. So we've got a matrix that is kind of pixels by features. And so I go -1, 9, and I look at that. Okay, and now we're at the same number of pixels, and we've got 9 features. So now we've made it here. I didn't want to do that. We've made it to our feature matrix X. All right, so now we can. So this is our inputs, but now we also want to get our kind of outputs, which we get from our target image up here. So target, we just kind of arbitrarily sort of did that little target. So how we can do that, it gave us a little tip to use np.ravel. So if I just look at what is np.ravel, and I'm just running this in the same cell, it doesn't really matter. So it returns a contiguous flattened array. So this kind of will flatten to a 1D array. And so let's think about for our targets, we call them Y, just in sort of common machine learning parlance. You have sort of targets or predictors at Y. So I'm going to grab my target. And now if I just did this, what do folks think might happen? If I just did this, now I've got 262,114 pixels, and I don't want that because I need to have this and X have the same length. And so what do I need to remember here? It's this. Oh, I didn't do that. I need to remember to grab just from the first to the one before and one to the one before. And so now if I do something like print x.shape, y.shape, you can see, all right, boom, back in business. We've got the same number of pixels in the input, each with 9 features, the same number of pixels in our target. And so we can start using scikit-learn to actually do this regression and identify our model coefficients. So what do they recommend? We recommend they use the logistic regression solver. So I'm going to import from sklearn linear model import logistic regression, and then I'm going to create a model. And again, if you're not familiar with scikit-learn, that's totally okay. This is just sort of supposed to be for a little bit of fun. And I'm going to create the logistic regression with a solver that is bilinear. So, oh no, not bilinear. Bilinear? Yeah, I guess that's. Yeah. And then I'm going to run model.fit, and I'm going to fit my x and my y, and then I'm going to look at my model.coefficients as they recommend. I'm also going to reshape them to be 3x3. Reshape 3x3, and let's see what we get. And boom. All right. So I've gotten -3.9, -7.19, and let's see. Okay. So what were we trying to get? So what would you think would happen? So we were looking at the Sobel H filter, and so if we think about the coefficients for the Sobel H, let's come down here. Sobel H. Okay, so that's 1, 2, 1, 0, 0, 0, -1, -2, -1. So that is a horizontal edge filter, and if we come here, we can see that we're sort of approximately following the right kind of orders of magnitude of 1, 2, 1 type of relationship. But we've also got some additional things kind of mixed in, some very small numbers here. These were all zeros in the other one. And, part of that is because we didn't have the pure Sobel H, we had this 0.07. And so, if we now wanted, though, to have a convolution filter that generated something a little bit closer to this, then we've learnt a convolution do that. Now, in machine learning, with convolutional neural networks, it's generally much more. You can have these like layers and layers of stacked convolutions as well, and you don't use just this simple linear regression to fit a regression and solve it in one go. You can use methods like backpropagation to learn convolution kernels that will get you from source to target. But it's a very, very popular approach. Things like UNets and stuff are special architectures, well beyond the scope of this particular set of tutorials, that will take you from a source to a target. So that was I hope people found that kind of fun. I said before, talked already about denoising filters, and we saw a lot around mean and Gaussian filters. Another really important one to know about is the median filter. And so the median filter, let's run this, is really nice because if you look at comparing the pixelated image, the Gaussian, and the median has actually done a much, much better job at preserving edges. And so it's done this because instead of looking at the mean within each set of pixels, it looks at the median. And the median is then much better at preserving a sharp edge, because you're not always like averaging, you're sort of taking the one, you're using a value that's present in the original image, and it's generally a nice approach. So the difference is, much more noticeable with the detailed image. We can run again, and you can see here, the median filter is it's still using values that are in the image. And you can see the nice coins. So that is it. I actually have to charge my computer. It's about to die. I'm sorry. But that is the end of the first lesson. And so we can take a break now for about 5-10 minutes. Maybe it's 1:02 now where I'm in my time zone. It's 2 minutes past an hour. Maybe we take a break for about 8 minutes, and then we pick up with the next lesson. And so for further reading, folks can go to the SciPy API filters. That's what I was poking around. The restoration module also includes really interesting methods as well. And so I'm going to stop sharing for a moment. Back now as well. And I hope folks have enjoyed that first lesson. I hope everyone sticks around as we start the second lesson. The second lesson is going to start going towards interactive image visualization and segmentation. I'm going to introduce Napari, which is a really cool multi-dimensional image viewer in Python. And I'm going to stop talking and catch everyone in 7 minutes. Thanks. All right, folks. I hope everyone that needed a little quick break was able to get a quick little break. See, there's some chats happening as well. But yeah, I hope folks enjoyed the first lesson on the basics of image filtering and kind of convolutions with scikit-image. Now we're going to pick up and go towards sort of segmentation and region props. I'm going to introduce Napari, and yeah, I'm going to take it from there. So I'm going to share my screen again. All right, to give it a second. So yeah, hopefully folks can see my screen. I see sort of infinite recursion, makes it look like it's going well. And yeah, let's close this tab and take us over here to the second lesson. And again, just a reminder for folks that are joining, this is the tutorials repository. Kira will be placing it in the chat as needed. And we've got all the lectures here, and there are copies with solutions and without solutions. And so if you want a little bit more of an interactive experience, you can go with the versions without solutions. If you just want to kind of follow along, you can look with solutions too. So if we start here, I'm again going to do a little bit of just kind of configuring my notebook, matplotlib. And let's talk about, segmentation. So what is segmentation? Separating an image into one or more regions of interest. If you think about Photoshop and you want to, extract one person and put them from one image into another, the first step of doing that is identifying where the person is in the source image. Pop culture, this example of the Terminator's vision, segments out the human from the overall scene. It's really, segmentation is just one of those basic things, a fundamental operation in scientific image analysis, because often we want to measure the properties of real physical objects. They could be cells. I would say my background's in biology, and so some of these examples might be skewed. And again. To bioimage analysis. And so, given that segmentation is so important, there are then questions of, okay, how can we identify objects with our images? So computationally, segmentations themselves are actually represented as images yet again of the same size as the original image, but now containing integer labels with one value representing one object. And so we're going to take this very simple image and segmentation from the scikit-image tutorial, which folks can look at. And let's run this here. And that's actually going to be quite a bit of stuff that's going to happen. And okay, so I've actually run this in. You see I've actually launched Napari as well. It's opened in a separate tab. Let me walk through a little bit about what we're doing here. So we've imported NumPy again, and the SciPy ND image, and then we've imported Napari. And then we've grabbed two functions from scikit-image, this watershed function and this peak local maximum. And so we're actually going to just generate an image now, and we're going to make just two overlapping circles. And so we can just see, I'm just going to make some indices of size 80 by 80, and then merge these circles as well. And if we sort of skip this little bit about the segmentation, we down here are instantiating the Napari image viewer, and then adding in an image as an image layer. And if I come back to Napari, I can look at this, and I can just see, all right, this is the image that we're looking at. It's these two circles, and in Napari we've got some of these functions actually be easier to introduce when we look at a real image instead of this this kind of simple toy one. So maybe I'll hold on a second before giving you a tour of the Nopari interface. But you can see already that we've got a canvas here and a camera, and we can move around as well. So, okay, if we want to separate these images, though, how can we start thinking about doing that? And a really great way to do that is with this approach called marker-based segmentation. And so we can first run a distance command to look at the distance of every pixel from the boundary of, well, let's say every pixel of where it's high to where it then goes low, and then we can look at a local maxima of that distance transform, and then find the centers. I'm actually going to do a little live adjustment here, because I think it's going to be even easier if I plot the distance transform for folks to look at actually at the same time. So I'm just going to pop in here, and I'm going to add in, I didn't even do this, I can just do this in another cell. So going off script a tiny bit, but I think it's actually going to be useful. If I come in here and I add in the distance transform, oops, where have I gone? Maybe I shouldn't have tried to go off script. Maybe actually I won't do that. Okay, so if we look instead at, we find the local maxima, and then we can label that mask, and then we can run our watershed using our distance transform. And the results of all of this are that we can see a label segmentation here of the two images. This is an Nopari context labels layer where we've got a 0, a 1, and a 2. So as said before, labels are really integer images. And then I can convert that to just being a black and white image as well. And you can just sort of view that interchangeably too. So this is a sort of a toy example. I'm not sure why I didn't like it. And I can look at that later. My apologies. It seems like there was some little bug there. But let's move on now to a real example with some cells, and I think that's going to be a lot more interesting. So when you downloaded this notebook, you also got a couple of TIFF files with images of cells inside them, and we can use this library TIFF file to read them. And so if we run this and look at what we see, we've got some images that are 60 by 56 by 56. And so you can think of this as a Z by a Y by an X. They're all between 0 and 1. They're floats. And the pixel data spacing of the data set is 29 microns in the leading axis, and then 26 and 26 in X and Y. So it's a little bit non-isotropic. And then we can, again, use Nopari now to view these. And if I come in here and I view in Nopari, I'm actually now in a 3D rendering mode. And so Nopari can do nice 3D rendering. I can also switch out of a 3D rendering mode into a 2D rendering mode. And I can come through here and look at different images. I can do things like change color maps. If folks want, you can also adjust contrast limits as well. A lot of the basics that you'd expect from an image processing tool, but one of the nice things is now that it integrates really well with the Jupyter Notebook. And so, you can go and you'll see some examples of bidirectional communication with the notebook as we go. So I got that image in there. I can actually use this screenshot functionality from Napari to take a screenshot, and that will run for a second, and you can sort of see, all right, taking a screenshot. Actually, yours might look a little different than mine because I adjusted the contrast limits. Maybe let me make the contrast limits a little bit nicer, and I could run that again, and it will take a nice little screenshot. And you can save those screenshots as well if you want. So just give me a second. All right. So let's now revisit some of the concepts that we talked about at the end of the first lecture around edge detection and the Sobel operator, and let's see what these now start to look like around for real image data sets. And so we can, again, import the scikit-image filters module. And we're actually now going to look at the SHA filter, which is a little bit more sophisticated. It's got smoothing weights, and both of these things work for n-dimensional images. So it could be 3D, it could be 4D, which is really nice. And so let's run this. You can see this Napari viewer object is persisted from the last cell, and so we can keep on adding layers to the viewer. And so we're going to do this. I'm actually going to change some of the properties on the nuclei layer. And you can see I can set some blending modes. I can set the color map to green. I can then add a new image and set, oops, is something?
Yeah, Nick, sorry to interrupt, but we're not seeing the Napari widget.
Oh, yes, that makes complete sense to me, because when I shared my screen, I only shared, it's a screen sharing permission. I will, thank you so much for letting me know. Otherwise I would have just kept on going and going and going. Okay. Let's see. Take two. All right. Can folks, let's see. So can folks see my screen now? They not an Napari screen, but can folks still see the Jupyter notebooks? Yes, I get some thumbs ups. Okay. Now can folks see the Napari screen? Can you see me looking at some cells, some green cells, magenta cells? Yes. Oh my gosh, I'm so sorry. Yeah, that was my novice screen sharing abilities. Okay. I do really appreciate the interruption there. I will, I'm not going to go back too far, but I will. It's cool you got to see the screenshot of Napari. But what have we done so far? So in Napari, we've just added 2 images now. I'm actually going to use the screenshot functionality again. But here's what the real thing looks like. And so as I was saying, you can come in here, you can do things like select color maps. I can, I think this was in green before. I can turn on, this is the edges. It's a little bit hard to see in 3D. If I go back to a 2D mode, you can see here how I've detected the edges using the SHA filter. Again, all sorts of nice 2D and 3D rendering capabilities. Adjusting, I think I called out adjusting contrast limits before, a lot of the interactivity and functionality that you'd expect from an image viewer. So let me just quickly check. Everything seems to be good on the presentation now, and we can pick up where we were in the notebook. So all things good. Thresholding. So thresholding is an incredibly important step along the way to segmentation, and it can be used to create binary images. And so threshold value can determine the intensity value separating foreground and from background pixels. Foreground pixels brighter than the threshold value, background pixels are darker. And in fact, for many images, you can do a pretty adequate segmentation by thresholding followed by labeling connected components, which is a fancy way of saying groups of pixels that touch each other. So different thresholding algorithms will produce different results. Otsu's method is a really classic one. Lee's minimum cross entropy threshold, it's another a very common one. We can use the Lee method below, but you can look in the scikit-image filters tab to find different thresholding methods. So first, we're going to do a median filter, though, to denoise the image. We talked in the past about the importance of denoising. And so now we can run the Lee threshold and see if to determine the threshold value, that's going to be a float, and then we can actually do the threshold here. And so if we add the threshold to the viewer, we can run the screenshot again, and some folks will see it, but let's go back. And you can see it's actually used wherever I was last to sort of take that screenshot. So this was, this was our image. We can look at the threshold, and you see we've done a pretty good job here at identifying a lot of the objects in the field of view. But you can see there are some holes, things are missing, there are some little small pieces, there are some things at the boundaries. And so now we can clean that up. And so morphological operators are just a great way to do kind of basic image processing methods and do that sort of cleaning. And so there's a little bit more at the Wikipedia page for morphology. And there are a lot of structuring elements in the find in the scikit-image morphology package. And, we've talked about structuring elements before. It's just another word for thinking about like a kernel. And so there's a mix of 2D and 3D structuring elements. Some have natural 2D and 3D correspondences, disk, ball, square, cube, things like that. Then we can run them on connected components as well. So we're going to look at two in particular, a remove small holes and a remove small objects. And both of these accept a size parameter, which is like a minimum size of accepted holes or of objects. So often in 3D, we might want to think about a linear dimension and take its cube. And so right now, we're going to remove holes objects of a cube of size 20 pixels across. So let's import these. Let's run this remove small holes. Let's run this remove small objects. And again, we can take a little screenshot here, but it's really much cooler to look at it in Napari. And now you can see that if this was our version, as was, our cleaned up version now looks like this. So we've removed, we filled small holes. So we didn't quite fill all these ones. These were big holes, I guess. And we've removed some small objects as well. So, coming along nicely towards cleaning this up and doing a segmentation. I'm going to look at the chat for a moment, just see how things are going. Okay. Looks like we're back on track. That's the other course. Let's go here. So segmentation. So now that we've identified these objects, we're going to be ready to sort of label some of the connected components of the image. So if we look at we can use from the measure module, this label object, and we're going to use the remove objects image. That's the image after it's been removed. And we're going to add that to our Napari viewer as well, and we can take a screenshot. And so let's come back to the actual viewer though, and see, it's done a pretty good job actually. So we've labeled now all the connected components. And so you can see that like this has gone its own color, this has gone its own color. These two have actually become one thing. I guess they must be connected somewhere. If not on this slice, maybe, oh, there you see it, and they're connected there. So they've become one thing. That's not so great. similarly, these things, they've all gotten one color, so they must be touching somewhere. So labeling connected components has, done a good job. Let's go back to looking at this a little bit in 3D. You can see here, we're actually working on some more advanced rendering and lighting modes for Nipari for labels. That will be out in the next release as well, so they should get a little bit nicer. Right now, these are all don't have any shading associated with them. Yeah, so that will, but we need to somehow deal with the fact that these cells are still connected. So if we come back and we think about, all right, so we've done a good job, but yeah, a better segmentation would assign different labels to different nuclei. And so we can go back to that idea of the distance transform and the watershed that I kind of introduced a little bit at the beginning, and now take and distance transform again of the objects. And if you want to read more about the distance transform, you can look at the NDI, the help for the distance transform, and it will explain exactly how it's working. Oh, I'm getting a little spinning thing on my computer. So let's run this again, and I can now actually use a points layer on Nipari to add in the maxima. And so I can take a screenshot, and let's look at this. And so, okay, so, you can see here, ideally we'd be in a situation where I was getting 1 point per cell, but, you can see I've actually got, many points per cell, and it's we need to somehow improve that. So I think now we've got many markers found within each nuclei, but I'd want to just find one marker. So the next exercise is to improve the points, and so some ideas are we could use a smooth version of the nuclei image. We could smooth the distance map. We could use morphological operators. We could change the min distance parameter of the peak local max. We could maybe find points on a single plane and then project them. So a lot of different options. And yeah, I'll give a little bit of time now for folks to kind of put in a solution, and then we can try some things together as well. You see how the Slack is, how the meeting's going. Need to apply the segmentation function to real data set. All right, let's try a little bit of this together. So, where do we think we should try things? So it looks here like we're getting many points, and that we shouldn't be getting. And so that tells me that we probably want to do some form of smoothing, and it's probably actually going to be best to smooth the thing right before we send it to the local maxima transform. So I'm just going to copy this over, as I think we're going to be reusing a lot of this. Maybe I'm going to rename this beta points, as hopefully they're going to be a little bit better. But now, rather than just using the transform data directly, I'm just going to use the filters.Gaussian, and I'm going to use that with a size 10. So let's run this, and let's go over to Nipari and see what has happened. I maybe should have made these points a different color, but it's okay. So if I look now at in 3D, you can see how this is much better. Here, maybe I can change the color. This, maybe I'll just leave it like this actually. And so you can see how it's gotten much better for these points versus versus these ones. Okay, so now that we've found our markers, let's we can actually here is the command to actually add them. So apologies, I've sort of done this too, but we can also add points manually. So if I create a new points layer here, I can actually use Nipari. I'm going to change the color. Maybe I'm going to use this red for the points. And now I'm going to add points. So I'm now in an add mode in Nipari. You can see I'm in a 2D, and I can just kind of come and click and click and click and click. And so, for a small image, it's actually not that big a deal to just kind of go through and add points as well. You can kind of see back here. Now I've got points as well. So that was pretty quick too. And again, one of the nice things about Nipari is you can do this kind of manual interactivity as well. So let's come back here and take a little screenshot. If you folks, want just some good points, you can just use this as well. Either way, if you have already done annotations, but you can also just use this too. So now that we've got the marked points, now we can go back and we can grab the data, and we can use the points as markers for our watershed segmentation. And so if we run this again, and we now use the points as markers for the segmentation, we get out a segmented, and we can add them to Nipari. You can see here we've actually done a much better job now. So you can see that we have, whereas the old segmentation down here had these three all together, the new segmentation with the new markers has gotten these things separate. So much nicer now. And we can even take a little screenshot of that. And so, so that's, that's an example of a marker-based watershed segmentation on a real data set, either using a little bit of manual interactivity to define the points in the GUI, or using concepts like a distance transform and filtering and a peak local maximum to find the centers of all the cells as well. So that was a little bit about the cells, but now that we have the cells, the next step is to make measurements. So we can actually do this using the region props or the region props table method, and this will give us a lot of simple measurements and features like area, volume, bounding box, intensity statistics, things like that. Before measuring, it's generally good to clear objects from the image border. I think measurement should only be collected for objects that are entirely contained in the image. Otherwise, you'll get sort of spurious results. Again, edge effects of a different type. So we also want to clear objects not only that are touching the side, but the top and the bottom. And so we're going to pad and crop the volume along the 0 axis and as well. So if we do that, we can then run clear border, and now we can use the region props to look at some properties of our cells. Now, not all properties are supported for 3D, so we can kind of look and see, what is supported for 3D and what's not. So supported properties, the bounding box, the area. Unsupported properties, sort of eccentricity, that doesn't generalize well to 3D. There are also, in recently Scikit image releases, support for passing some custom functions as region props. So, you could augment this list too. And region props, it ignores the 0 label, which represents the background in the image as well. So as region props returns a dictionary of columns, we can actually really easily convert that into a pandas data frame, which is a really nice package for pandas, a really nice package for looking at tabular data in Python as well. And so we can just grab a few properties: label, slice, area, mean intensity, solidity, and label is not the the property. And then if we look at this table, we've got a nice, just to look at the top of it, the head, we've got a nice little bit of information about the slice. So, the area, the mean intensity, the solidity. And now we can use pandas and seaborn for a little bit of analysis. So if we make some plots, you can see, okay, most of our cells are up here. They vary in size, but they tend to be pretty solid, have a good solidity. But then there's one outlier right here. And if we go back to our data set, and we look at actually what did we see in our data set, all the way back here, you can really clearly tell there's one very clear outlier that's not as solid as the others. That's this one, and that's the mitotic cell that's in the process of dividing in half. And so here, we've obviously, it was something that was obvious to us in the visual, our visual eyes, but we've done an automated analysis now that allows us to really clearly distinguish the dividing cell from the other cells. So maybe as a little exercise, folks can think about adding a new column to the data frame with area in microns cubed. The area is actually just a measure in voxels, and maybe we can use the scale information from above to put that in a physical unit as well. So I'll pause for a moment, let folks that are interested in trying this try this out, and we can, I'll monitor the chat for a little bit, see if it's going okay. All right, so let's give this a try. So if we do info underscore table, and then what did we say we call this? Area underscore micrometer cubed. And then we can grab the actual area, which I think was area. And then I do believe it was times 1.29 times 0.26 times 0.26. And then if I just do the same table area, just to look at it. Oh no, what is it? Info table, info area, info table. You can see here the area in microns cubed. So volume actually, it's a little bit maybe of a misnomer here. It really should be called volume in some senses too. So some potential exercises now, and I think some of these can be left for exercises for interested folks to follow up on after. We can people can try a little bit right now in real time. We're actually making really good time right now, so we have a little extra time. But we loaded the membranes into memory at the very beginning, but we have yet to do it. And so we could try and use that to segment out full cells and add the segmentation to the display. And I will pause for a moment. And I think this is we're maybe not going to do this full one now in real time, but let me pause here for a little moment. So let's come back up here and let's at least look at these membranes. Where did we load them in? Nope, not here. Here, we loaded them in here. So we just called the membranes. Okay, nice. I'm going to come down here, make a new Napari viewer, and then need to So I've made now a new Napari viewer. I just loaded them both in as black and white. First things to do, let me adjust some color maps. So let's make our membranes magenta. Let's make our cells green. Right now you don't see anything because they're actually being overlaid. They're not being blended. So I can come in here. I can make them blended more a little bit. And now you can see, I'm going to put the contrast limits of the membranes down a little bit. And so, you can now see it's like a much more challenging segmentation problem to attempt to try and get the full cell boundaries of the cells. And actually, we're not gonna try that right now together. But this is just another example of looking at data together, and something that folks want to spend some more time on their own after these tutorials. Doing more could be a great thing for them to try. There's also an exercise here that I think I'm going to leave to the reader as well for afterwards, which is looking at additional overlays of values from the region props on top of cells as well. It could be a fun exercise left as well. So that actually, this lecture went really quickly. So I think we've been making really good time here. Maybe let me stop sharing again. We can take another a short break now, maybe another like 10-minute break, and then we can move on to the Dask lesson as well. But I think we're making very, very good time right now as well. And if there are any particular questions in the chat as well, I think we'll have some time for discussion at the end too. So it's coming up on 47 minutes past the hour for me. Maybe we have a little break until the hour and come back in 13 minutes, and then we can pick up with Dask and the Dask tutorial. All right. Hope that sounds good to everyone. All right. Hey everyone. Hope everyone's doing well. With that now, I'd like to pick up on our third lesson, which will be introducing Dask. And so this is the third notebook, and let me pull it up here. Let me share my screen as well so that everyone can see. I'll make sure to share in the Napari compatible way as well. And all right, so I think that's picked up there. And yeah, here we are. So out of core image analysis with Dask. And so one of the big things just to kind of note is that images can tend to be really large. And oh, actually, before I dive into that, there was a little thing I think in one of the previous questions in the Slack about turning visibility on or off, and I can revisit that when I have Napari open. But sorry. So images, can get really, really large, and so sometimes we need methods to avoid using or to allow us to scale to large images. And so one option is to leverage Dask. We can also leverage Dask distributed as well, which actually gives you access to a diagnostics dashboard that you can open up as well. Let's see if I open up the diagnostics dashboard. Yep, so right now this little Dask diagnostics, so far I'm not using anything, so nothing is here. We can read a little bit about the diagnostic dashboard on the Dask website, but you can think of Dask as a generalization of extension of an array library like NumPy, but to now work in a distributed fashion. So it could be an institution's HPC or a cloud compute, but the API is just the same regardless, which is really nice. So, first we can see, let's just import Napari and check we can still use Napari, and folks can see. All right, so hopefully everyone should be able to see my screen here again. And just a note, in the notebook, these are just sort of screenshots that are static that you cannot interact with, whereas the actual Napari has opened up in another browser. One thing that came up in the earlier lesson was toggling the visibility of layers. You can see this little eye icon there allows you to turn things on and off. I just want to quickly check the chat and see that everything is good. Yeah, I don't think everything is good. So yeah, no, press on. All right, so Dask allows you to look at large images. So let's see if we can try and view an impossibly large image. So and where impossible means sort of, having the full array of memory would be, bigger than a terabyte of RAM. And so we can do this by, we can sort of create this sort of impossible image. And don't worry, we've not actually created something that is more than a terabyte of RAM here, even though if we had all the bytes, it would be. You can actually see here, we're not doing anything yet. And if we try and view this in Napari, you can see that we're actually able to, so this is our impossible image you can see here, and we can sort of zoom in and out, and we can even actually scroll along it with the slider, all 40,000 time points. But what's happening is every time we move the slider, we're dynamically, in this case, computing or lazily computing just the random numbers that we need to see here and displaying on the screen. And so that's really nice because it means Napari doesn't actually ever have to have the full data set in memory. It can just have the individual piece that you're trying to look at. And in general, we try and use concepts like that to ensure that we scale to large data sets as well. So we can come here. I'm actually going to come back. I can close these Napari windows. I'm going to use them again. And my apologies, actually really should have remembered to give people a heads up about this, but in the installation instructions, there were some links to a couple of extra data sets, either like a 3 gigabyte or a 98 megabyte data set. maybe folks that want to try playing around with some real images can download the 98 megabyte one in the meantime. How long it takes to do the 3 gigabyte one. Apologies for forgetting to give that reminder before the break. That was my bad there. So we're going to use the Dask image library, and that's got an imread function, and you have to set a root path to where your data is living. I'm using this one from that cell tracking, this Fluo and 3D. I think it's the C elegans one, CE, so C elegans. So I set my root path, and then I load it. I'm actually going to downsample it a tiny bit. I sometimes on my laptop have a bit of a ghosting issue that I need to fix if I have the full data set and with everything. And so we can see what this is. Okay, it's that's great. Actually, if I just type in embryo, Dask has a really nice wrapper now that you can see everything in. So you can see that we've got 250 chunks along the first dimension. The chunks are 1 by 3 by 35 by 254, 354. So each volume is its own sort of chunk, and that's because each TIFF file here was its own chunk, and it was a volumetric time series of data. So we got 250 chunks. If I go into my Dask status, actually here, you can see that there are a variety of things happening as Dask is loaded in data as well. But we don't have to worry about that too much right now. So let's just try and look at this data set. So if I look at the D type, there's a UN8, the number of bytes, this is, it's only 0.7 gigs, so it's not that big. But still, it's kind of nice that we can just look at this. And so if I go over to my Napari window now, I can look in Z here, I can see, and then I can also look in time here as well. I can actually look at this in a 3D rendering mode, and it's maybe a little clearer what's going on. So it's a little noisy, this image. You can also see there's some anisotropy, but it's a C. elegans embryo that's dividing. So here we've got 1, 2, 3, 4, 5, 6, 7, 8, cells, and then over here, now we've got more and more, and we can look at it through division 2. Actually, should maybe adjust the contrast limits as well. So that's a little bit about that data set. There's an exercise here which I think we can leave again as a one for after the tutorials if folks want. But instead of leveraging the TIFF files, we could actually use the ZAR file format to save our array to ZAR, and then we could reload it, and that will be much faster as well. Maybe if folks do want to try that, they're more than welcome. So now I want to show you some stuff about tracking data, and so this data from the Cell Tracks website contains some tracking information. I also have to downsample it a little bit, and we can get these little tracklet images, and then we can use the same region props that we were looking at before to get some properties like the centroids, and this function, we now want to run it on every single volume, so it takes in a volume our function, and so we can use the client map API to map this function across all of our data. And in general, one of the nice things about Dask is that you can make these function calls, but they don't necessarily trigger computation immediately. Computation can be sort of triggered lazily, which is really nice. And again, it kind of comes back to that idea of Napari of just sort of waiting till the last minute to trigger a computation and a load. So if we run a map, we can then actually get the result. So this is where we're actually, this thing ran instantly because we weren't actually running anything. now we're getting the results. So now we're running this. And it will take just a moment, shouldn't be too much longer. And then once it's done, we'll be able to put all the tracks information into a bigger table, and then we'll be able to add the tracks to Nupari, and we'll sort of see in a moment what that then looks like. So if we add the tracklets here, and then we're using a tracks layer, and the tracks layer, there's some really nice stuff we can do with it. So you can actually come into Nupari as well, and so you can see here there's a tracks layer, and they update in time. It just sort of, you can see a little history into like how the cell was moving. In here, they're not moving as much, and out here as well. So you can go in here, and there are various rendering modes. I can try and make this looking a little bit nicer as well. That's saturated there. That's interesting. Maybe if I come in here. Okay. Yeah, but at the end, the raw image is saturated because I guess they compressed it. And so we can also look at different color maps as well. It's pretty cool. You can see the cells around too. And underneath this now, it's a Dask array that's sort of lazily loading in each time we move as well. So there's also the tracks layer, and that cell tracking data set can support lineage information too. And so we can get different columns of labels, either the unique label or where the track begins and ends, and then the parent track as well. And we can load that data in, and now we can add a tracks layer with a little bit more detail of a graph that sort of shows how cells relate across cell division. And so I can sort of come back in here. You can see, there's a little bit more of how the cells relate too. So that was a little bit about Dask and tracks and cell tracking. The final sort of challenge is we want to maybe look at some cell segmentation. We can also do some filters from Dask image. So in the same way that SciPy had some filters as well, we can use the Gaussian filter from Dask. We can give a scale as well. The 0 means we're not going to filter in the time domain. So let's try running this as well. And we can see how this is now much nicer than before. So it's going to be much easier to do a segmentation on this. And let me come out here. It's quite simple. Come back here. So, it's blurred for sure a little bit from the Gaussian. Maybe we should do, median filtering instead. We can also use the map blocks to just find the edges. So again, it's the same sort of concept now, though we're actually going to use the SciPy SHA filter, and we're going to use the map blocks to map this function across all of the chunks in the smoothed array, and then we can add this again. And so, again, we're building the same sort of concepts that we've seen all the way through from 1D through to 2D, and now through to 2D that is bigger than fits in memory. And so, oops, I'm getting a little thing here. And so now you can see that we found some edges as well. And so, this is stuff that we could use to put inside an additional segmentation as well. So, we could, there's some challenges here that are open. We could find some threshold values for each time point using the smooth data. We could use some NumPy broadcasting and the add to the array. You can also use map blocks to do some custom filtering, or even go all the way through the map blocks with the scikit-image watershed that we did on the previous function to create a labeled array as well. That was that was sort of the end of the prepared content on the Dask tutorial. I actually thought a lot of today would take a lot longer than it ended up doing. So we've run through time very, very well here. Maybe I pause. Let's see if there's stuff happening in the chat. Can you talk about the data you're using? What are they? Yeah. So that data was from cell tracking competition. It was a C. elegans embryo, so a little worm that was dividing, and it's just sort of nice because you get to see the cells in 3D and a time series, and volumetric time series is becoming more and more common in the imaging and microscopy world. So that was sort of it. I'm going to stop sharing for a moment. Yeah, so we have a lot of time left, obviously, everyone. I do apologize. The prepared content I had definitely ran shorter today. I'm happy to though move to a little bit more of open discussion and Q&A style things. I think there are ways that we can bring folks kind of on stage as well if they have questions. I have some discussion questions that we could talk about in the fourth Jupyter Notebook. Maybe let me share my screen quickly again. Some of these things relate to other things about Nupari or scikit-image or other file formats. Yeah, we'd be very happy to touch on any of those things. There are questions in the chat. Other questions in the chat now is also a great time to ask. Otherwise, we can also, wrap up. I mean, it's really SciPy. There's a lot of great stuff going on, and I know there are other tutorials at the same time slots. Maybe I think there is even a Dask tutorial at the same time slot. If folks want to hop off and go to that. But again, if there are any other burning questions. In and out. So I have a question in the chat. Let me read the question and then we can discuss it. So I've been in and out, so you may have missed it, but are there tools for annotating and viewing image that work with a notebook? I have a Jupyter Hub deployment that is headless. Don't want to bring in Qt. Yeah, so it's a bit tricky. Unfortunately, right now, what I showed you with Nupari will not work. There is, I think I would probably recommend that you investigate Pixamy. I will put a link for that in a chat. It's a very new annotation tool. I'm not quite sure about its Jupyter Notebook integration, but it's I'm sure it's something that team is thinking about. So let me pop that in the in the chat. I've got the GitHub well, here it is. So all right. So yeah, iPy volume Pixmy. This one's nice. Yeah, if you're drawing, here's a little announcement on it too. I can even. All right. Are there any other? Yes, I think there was also a shout out for iPy volume for 3D viewing. Yep, that's another great tool, and I think it's really interesting. I mean, for Nupari, we were using Qt there. Definitely a lot of other interesting approaches that one can take, that Jupyter Hub use case is a really important one for sure. So. How is the performance of a larger 3D data? Okay, well, it's Napari right now. We don't have anything that scales to really large 3D data sets. So we don't have any concept of tiled rendering or octree-like rendering for large data sets. It's something that we want to work on, we want to add in, but we don't have yet. I think if you're looking for viewing really, really big 3D data sets, your best tool right now is probably NeuroGlancer. And so I'm not sure if you're familiar with NeuroGlancer, but I can put a link to that in the chat too. And that's a WebGL-based tool that's really designed from out of the box for going for like really, really big ones. White team got mentioned. Yeah, I'm not, that maybe for the annotation, I'm not sure, but for really big ones, we definitely want to work on that in the Napari for sure. It's, so, hopefully something that will be coming soon. But for now, if you have really, really big ones, I'd say you might want a tool like NeuroGlancer.
Okay, Nick.
Hey, Eric. I think we ran pretty quick through today. I hope it was really good for everyone else, though.
Very informative. I learned more about Scikit-Image than I knew before, so that's always great. So thank you.
Wonderful.
You seem to have dried up on your questions, so I just say let everybody go about their business and find something else interesting to sit in on or discuss with other people. So
yeah, and I'll be around if you want to ping me in the Slack on the I'll be there, and happy to answer more questions offline if things come to people's minds. So thanks very much.
Great. Thank you.
Bye-bye.